Howdy! This is your friendly neighborhood physics teacher here, and today we're going to talk about Newton's second law. So, force, mass, and acceleration and the relationship they have with each other. This law is not new. F equals ma. May the force equals mass times acceleration be with you. Your formula chart just writes it a little bit different, right? So that as acceleration equals the sum of the forces over mass. This little arrow means that your acceleration is a vector. We know that. This little arrow means that the force is a vector. We just learned that. Remember, epsilon is the sum of. Your second law is basically this equation. So for your metric units, for force is in newtons, mass is in kilograms, acceleration is in meters per second squared. If we're looking at the imperial, the English, force is in pounds, mass is in slugs, and your acceleration is feet per second squared. Now, if we put a small force on this 1 kilogram mass, therefore it's a small acceleration. If we put a big force on this 1 kilogram mass, it's a big acceleration. Same force, some force, your acceleration is 1 meters per second squared. This is a direct relationship. As force increases, your acceleration increases. As force decreases, your accelerations decrease. That is a direct relationship. So if you have 1 meters per second of acceleration, you are putting a force of 1 Newton on that 1 kilogram, which makes sense if you put it into your equation. 1 meter per second squared equals 1 Newton divided by 1 kilogram. It gives you that. Because, remember, Newton is just a combination of kilograms meters per second squared. Newtons is the common unit. Your kilograms meters per second squared is your MKS unit, or your SI unit. So again, we have 1 kilogram. What would be its force of gravity, or its weight? But on Earth, your acceleration is 9.8, technically a negative 9.8 because it's going down. So for 1 Newton, the amount of force needed to accelerate a 1 kilogram mass at a rate of 1 meters per second squared. That's basically what 1 Newton is. So therefore, since our acceleration is 9.8, our force of gravity is 9.8 newtons. Should be a negative because it's going down. So 1 kilogram weighs 9.8 newtons. We already kind of assessed this when we went over mass versus weight. Just kind of showing you how it relates to the equation. So again, net force equals our mass times acceleration. That's what we're used to seeing it as. But up here is how your formula is written on your formula chart. Force of gravity or weight is the exact same equation, it's just being a little bit more specific. It's using the acceleration due to gravity, a constant, when you're on Earth. Like I said, gravity and your weight is the exact same thing. So you have a weight that is either 20.4 kilograms or 45 pounds. That's force, that's your mass. So your mass would be the 20.4. You're multiplying that by 9.8, and you get the fact that's 200 newtons. You could use the conversion to figure that out in pounds and see if it's close to 45. So, things I want you to be able to do is identify the 4 unique quantities of Newton's second law of motion, or implementations. So the first one I want to look at is that the acceleration is inversely proportional to mass. Now remember, inversely proportional means as your mass increases, your acceleration decreases, which makes sense. Heavier objects or more massive objects are harder to move. Your acceleration is directly proportional to force. So your acceleration increases, your force increases, vice versa. If acceleration is equal to 0, if and only if net force is equal to 0. So your acceleration is only equal to 0 if your net force is equal to 0. That doesn't mean that there's no forces on the object. It just means that your net force is equal to 0. That means it's at equilibrium. Go back and rewatch the equilibrium video if you really need if you need a refresher, because remember, all forces are balanced at equilibrium. And then the acceleration is in the same direction as the net force. Net force and acceleration are in the same direction. So let's focus on the acceleration is inversely proportional to mass. A force is applied to a 2 kilogram mass, producing an acceleration of 10 meters per second squared. So same force. So if we have a 4 kilogram mass, how would that affect our acceleration? Would it increase or would it decrease? It would end up decreasing. Remember, it's an inverse relationship. As your mass increases, your acceleration is going to end up decreasing. So our mass decreased, so therefore our acceleration should increase. So let's look at here, where these numbers are coming from. So we're looking at force equals mass, write it up a little higher. Force equals mass times acceleration, right? So let's figure out what our force should be. So if our mass is 2 and acceleration is 10, our force should be 20 newtons. So if it's the same force, our force is 20 newtons. So again, for force equals mass times acceleration, our force is 20 newtons, our mass is 4, our acceleration has to be 5 to make that work. Using the equation again, same force is 20, our mass is 1, so therefore our acceleration has to be 20. So let's look at this one. We have force equals mass times acceleration. If our mass is 20, or our force is 20, our mass is 20, that means our acceleration would have to be 1 to keep things balanced. What about 8? Our mass is 8, getting to 20. Our acceleration, just divide, our acceleration will end up having to be the 2.5 for it to balance out. So your acceleration is inversely proportional to your mass. So if your mass is 100 kilograms, add what would your force would be if your acceleration is 10? So we have mass. Remember, force equals mass times acceleration. So you're just multiplying the two. So our force would end up being 1,000. Now we've increased our mass. We put that same engine into the car as the engine of the motorcycle, it'll have the same force. But our acceleration, because we're increasing the mass, the force is the same. Trying to put a unit on the end and it's not allowing me. Therefore, our acceleration would have to be 1. Because acceleration equals our force divided by mass. So now if we do it again, we have a big recycling truck, that same force. It's really not going to be able to move, right? It's going to be crawling. So now we're going to move over that our acceleration is proportional to force. So if a force is 5 newtons and produce an acceleration of 10, what would be our mass? So again, our force equals mass times acceleration. Force is 5, we're looking for mass, acceleration is 10. So our mass would end up being 5 over 10, or 1 over 2, or 0.5 kilograms. So now we're looking at a force of 10 newtons. So again, F equals ma. Our force is 10. Our acceleration is 20. So our mass would end up being 10 over 20, which just ends up being 1/2, which still is 0.5. We still have a change of the same. So your force increases, your acceleration increases if your mass stays the same. So normally an aircraft accelerates at 2 meters per second. If one of the 4 engines fell, how fast will it accelerate? So an engine fails. End up getting 1.5. Whoops, go back. The reason it's 1.5 acceleration is because we're going from 4 engines to 3 engines. So if there's 4, okay, so if we're moving at 2 meters per second squared. Color so you can see. This one's a little bit just more figuring it out. So if we have a 2 meters per second squared, each engine, so there's 4 engines, so each engine is responsible for about 0.5 of that acceleration. Well, if we lose 1, this goes down to 1.5. Kind of way to think about it. So now we're going to jump to the acceleration is 0. So again, this is going back to equilibrium. So if the net force on the refrigerator, so what is the net force on the refrigerator? So he's pushing at 50 pounds, and the velocity is 2 miles per hour. The hint is velocity. Hint is velocity here. Friction would be the same, because it doesn't say it's accelerating, it has a velocity. So that means friction would have to be a perfect balance. So friction would also be 50 pounds going against the motion. So your net force would end up being 0 because the forces are balanced. So a rocket is being accelerated by a force through space when it suddenly encounters an equal force in the opposite direction. The ship will be brought to a rapid halt, slowly come to a stop, continue at the speed it had just before the second force began. So think about it. So the rocket is being accelerated by a force. So pretty much the force of thrust, or the force of the engine, It's making it go faster and faster and faster and faster and faster. So so if we're doing our free body diagram, so if we do a free body diagram, so we have a force applied going this way by the, keep getting too close to the edge here. We have a force applied caused by the engine. All of a sudden, we have some type of force, let's just say force of friction, that hits it. And it's the exact same as your force applied. What happens? Hopefully you pick C. It just continues at the same speed. The answer is C. So now, because the forces are balanced, it's just going to keep going at the same speed as it was the instant the second force jumped in. It kind of look like this. So it's going to be accelerating, 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 and then as soon as that second force kicks in, it's going to stay at that acceleration. So to jump over to the acceleration is in the same direction as the net force. So if you're in the car and you push on the gas, that's a force applied to make it go. The force is going in that direction, so therefore the acceleration is going in that direction. Now, if you're braking, you're adding a force to the wheels to slow you down. That force is going backwards, that's slowing you down, so then the acceleration is backwards. Same thing with gravity. You throw a ball up, it slows down and then speeds back up, all because gravity. Acceleration is always down. Okay, so in Mission Impossible 3, this is the bridge when the jet is going around blowing things up. We have this force of the explosion is causing him to accelerate off to the side. Now, this is a case where it's still going up and he's still going forward, like towards your screen, but he's going kind of at an angle because the force affected him at an angle. Okay. So we're going to find the acceleration of the system. We have a 70-gram little car here, and it's being pulled. It's tied to a string to a mass that is 200 grams. And this little frictionless pulley here just kind of guide the string so it doesn't get caught on anything. So as the force of gravity is pulling it, so the force of gravity of the 200-gram mass is 1.96 newtons. You got to convert your grams to kilograms and then just multiply it by 9.8 because that's the acceleration due to gravity. Now, it's not just accelerating the mass anymore, this mass. It's acceleration both masses. So it's not going to be moving at 9.8. So the force is 1.96, but it has this extra mass. So to figure out your acceleration, you have to add that extra mass to it. Of course, converting it to kilograms. So find the tension in the string. You're still using your F equals ma equation. You're just focusing on the top part, not necessarily the bottom part. We know the top part is accelerating at 2.818 because that's what we solved for. But this tension is only being affected by this mass. So we're able to figure out the tension that way. If we're going to figure out this tension, again, we're just worrying about the bottom mass. So you would use your F equals ma equation. Now it's accelerating downward, but as this object has two forces. It has the force of gravity and tension to the mix. Tension's going up, force of gravity is going down, so you do have to subtract force of gravity to the tension. And lo and behold, guess what? The tension's going to end up being the same. If it's the same string, tension is the same. If it's the same string, tension is the same. Say it one more time. If it's the same string, tension is the same. This is called an Atwood machine, when you have two masses hanging from a pulley. So if we are going to try to figure out, that's kind of how it works. So we have one mass, that's 20.4 kilograms. We have another mass, that's 11.3 kilograms. It makes sense that the heavier mass went down and the smaller mass went up. Both of them do have a force of gravity. Obviously, the one with the more mass has a larger force of gravity. Just take the mass, multiply it by 9.8. But each of them have a tension force. You can actually make this one big system. It's connected. So think about this one is being pulled that to the right, this one's being pulled to the left. I understand they're both being pulled down. Since it's one string, you can think about it like that. It makes a little bit more sense. You can redraw it. So you have one force that's causing the motion, which is the 200. That's why it's going, the object was going in that direction. And this 111 is kind of counteracting this motion. Without that, it would go and hit the ground really quick, right? And you have to take both masses into consideration. And you get a 2.81, sorry. Now this is just a machine that's going to pull up the 11.3 kilograms at an acceleration of 3 meters per second squared. So we still have a force, and we have a force of tension because there's string involved. Our force of gravity is still 111 because we're using the 11.3 kilogram mass. If we were going to try to find the force of tension, you have two forces there. You have to take both forces into consideration. Tension is positive because it's going up. Gravity is negative because it's going down. But in this case, we're only dealing with one mass. So you can do algebra and figure out what tension is. So that's basically meaning that the breaking point is 2 kilonewtons. So if our breaking point was 2 kilonewtons, which is 2,000 newtons, is kilo, bring it over, convert, how fast would the machine have to go to break it? Let's figure it out. So again, you have force of gravity, force of tension. So if it's going down, our acceleration is negative because acceleration is a vector. Again, do math. And you get that the fact that the tension is 77.1. I feel like I missed. Did I not give the answer? I am so sorry. This answer did not appear. So how fast would it have to be going? So you would take your 2,000. I just now realized the answer did not pop up. So you're going to take your 2,000, subtract that by your 111, divide that by your 11.5, because that's the only mass you're dealing with. And to make it break, you would have to move it at 167.17 meters per second squared. That's extremely fast. So it does have a high tolerance. We just did this problem. So going up, tension is stronger, makes sense. Going down, tension is less. And there you go. So you do have some practice problems to do. If you have any questions, please let me know. Have a wonderful day. Bye.